Welcome back to the Curious Mind GATE-2013. In this video, we are going to learn to ascertain whether all the eigenvalues of a symmetric matrix are real or pure imaginary or complex with non-zero positive imaginary part or complex with non-zero negative imaginary part. Using this question as a learning reference, which is from GATE 2013 MESAT, which asks about the nature of the eigenvalues of a symmetric matrix. While there may be a property of a symmetric matrix that can answer our question, most of the viewers often unable to recall that property. So for those viewers, today we will use the most versatile method, which is the verification approach, by considering an arbitrary second order symmetric matrix and then try to determine its eigenvalues to answer our question. One thing to note here is that while we can choose to consider any order of symmetric matrix for this verification approach method, we are considering second order symmetric matrix for simplification purposes, as it would be easier to find the eigenvalues of a second order symmetric matrix than those of a third or higher order symmetric matrix. Also, I would like our viewers to recall that a square matrix has a same number of rows and columns in it, and a symmetric matrix is a square matrix whose elements are the same across its main diagonal. In other words, a symmetric matrix is a form of a square matrix that is identical to its own transpose. So let's consider an arbitrary second order symmetric matrix. So there we have it, symmetric matrix. So it's a second order symmetric matrix because it's a 2 by 2 square matrix, meaning it has two rows and two columns, and the elements across its main diagonal, which is this, are the same. In the same manner, We can also write an arbitrary third order symmetric matrix just for the understanding how a symmetric matrix of order 3 would look like. So we have it third order symmetric matrix. It's a 3 by 3 square matrix with 3 rows and 3 columns with elements are the same across its main diagonal, meaning 4 is equal to 4, 5 is equal to 5, and 6 is equal to 6. So it's a third order symmetric matrix. But we do not need third order symmetric matrix for our verification approach method. So we will just remove it. But we would need a identity matrix of order 2. So we would write its matrix form. Now we need this second order identity matrix to set up the equation that would be needed to determine the eigenvalues of this matrix A. So now we would write the equation. So we have it, this equation. It's a matrix where lambda is the eigenvalue of matrix A and I is the second order identity matrix. So before we plug in the values of matrix A and the identity matrix I would like to explain that A minus lambda I is a matrix and the determinant of this matrix is equal to 0 gives the eigenvalues lambda of this matrix A. So now first we would write the inner matrix by plugging in the values and then we determine the determinant of this inner matrix and set it to 0. Okay, so we have the plugged in expression in which we have plugged in the values of matrix A and the identity matrix I. Now we would multiply lambda into this matrix and write the expanded expression. So we have the next step where we have multiplied lambda through this identity matrix. Now we would subtract this matrix from this matrix by subtracting each element of this matrix from the corresponding element of this matrix and would write the next step. Now we have the simplified expression and now we will remove the inner matrix and directly set the determinant to 0. So we have the next expression, after removing the inner matrix and setting the determinant to 0 of the inner matrix, we can further simplify this determinant before expanding it. So we have the simplified determinant. Now we would expand this determinant by cross multiplying, because it's a 2 by 2 determinant. All right, we have the expanded form of the determinant. Now we would further simplify this equation by multiplying through. So we have the next expanded equation. We would further simplify it into a more simplified form. So we have the a simplified expression, which is actually a quadratic equation with a variable lambda. We can solve this quadratic equation either by factoring or by using the standard solution formula of the quadratic equation. Since factoring seems to be a little bit difficult, we would use the solution formula of the quadratic equation to determine the value of lambda. Now we have the value of lambda in this form, and this form is the solution formula based on the quadratic equation, which is this. So in general, a quadratic equation is given by this expression: ax square plus bx plus c equal to 0, and its solution formula is given by x is equal to minus b plus minus square root b square minus 4a into c divided by 2 into a. So by comparing this quadratic equation from this equation of lambda, the value of a is equal to 1, the value of b is equal to minus 3, the value of c is equal to minus 7. So we would plug these values of a, b, and c in this solution formula, and we would get this expression of lambda. Now we would further simplify this expression of lambda. After further simplifying, the values of lambda are 3 plus minus square root 37 divided by 2. So both values of lambda are real numbers. Alright, we can say that the eigenvalues of a symmetric matrix are all real. So the correct option is C. Now, if we were to consider any other second order symmetric matrix with other values than those we considered inside it, then we would also get the values of lambda other than those we got here, but those values would also be real. All right, so it does not matter that a particular values would only result in the values of lambda being a real number, because no matter what combination of values we consider in our second order symmetric matrix, we would always get values of lambda a real number. I mean both values of lambda a real number. Alright. Now this would also be true if we considered a third order symmetric matrix, or fourth order, or fifth order, or any higher order matrix. The values of lambda would always be the real, but the values of lambda may be different from those we got here. Okay, but those values would always be real. So the so this statement is always a true, that the eigenvalues of a symmetric matrix, no matter which order it belongs to, are all real. Okay.